Until the 19th century, calculating the speed of light meant looking to the stars and making educated guesses based on planetary orbits. But a small group of physicists decided to pull this phenomenon down to Earth and measure it directly. The challenge was immense. They had to trap the fastest thing in the universe, using nothing but the brass, glass, and gears available at the time. This meant moving the quest out of massive astronomical observatories and into cramped physical laboratories. Because light moves so incredibly fast, a standard clock or stopwatch was completely useless. Human reflexes couldn't click a timer quickly enough to clock a beam traveling across a room. To catch a pulse of light, scientists had to throw out the concept of measuring time with ticking hands. They needed to build mechanical traps that used continuous physical motion to freeze a beam in its tracks. The first successful trap was built in 1849 by French physicist Hippolyte Fizeau. Fizeau separated a light source and a distant mirror by 8 kilometers. A spinning gear chopped the beam into discrete pulses. After traveling the distance and bouncing back, the returning pulse wouldn't pass the gap, but instead hit the solid metal of the next tooth. By knowing exactly how fast the wheel was rotating and the exact distance the light traveled, Fizeau calculated the speed. He clocked it at approximately 315,000 kilometers per second. He proved it was physically possible to measure light's velocity. However, relying on an 8-kilometer gap in the open air was cumbersome and prone to atmospheric interference, requiring a much tighter indoor solution. 13 years later, in the year 1862, Léon Foucault improved on Fizeau's methodology. Foucault replaced the wheel entirely, bouncing light off a rapidly spinning mirror toward a fixed one, folding the experiment into a single room. As the mirror turned slightly during travel, the returning beam bounced off at a new, measurable angle. He refined the speed down to 298,000 kilometers per second. He also ran the beam through tubes of water, proving that light slows down in denser mediums. By proving light slows in water, Foucault's physical measurements directly supported the theory that light behaves as a wave, rather than a stream of rigid particles. In 1865, James Clerk Maxwell approached the problem without using mirrors or gears. His method relied on pure mathematics and the study of electromagnetism. In his paper, A Dynamical Theory of the Electromagnetic Field, Maxwell studied the electric and magnetic properties of free space. He calculated how fast an electromagnetic wave would travel through that space, based entirely on those physical properties. This side-by-side comparison shows the result. Maxwell's purely theoretical speed for an electromagnetic wave was nearly identical to the physical speed of light Foucault had just measured. The numbers aligned. Maxwell realized it wasn't a coincidence, leading to the conclusion that light itself is a form of electromagnetic radiation. Maxwell's discovery that light was an electromagnetic wave shifted the stakes. It was now a fundamental property of the universe. In the late 1870s, Albert A. Michelson set out to define it with a level of precision that hadn't been possible before. Michelson took Foucault's rotating mirror concept and scaled it back up. He engineered higher quality optical lenses and extended the path length between the mirrors to give the light more travel time, greatly reducing the margin of error. This precision scale shows Michelson's final 1879 result, 299,910 kilometers per second. He locked in a measurement that was within 0.05% of the modern accepted value. His exactness gave physicists the concrete mathematical certainty needed to start untangling the universe's mechanics. Over a few short decades, science evolved from making broad celestial estimates about light to capturing it directly on a laboratory workbench. Connecting the physical speed of light to electromagnetism eventually allowed engineers to harness the rest of the spectrum, from radio waves to X-rays. Chasing the beam gave us our first absolute physical constant. Measuring this velocity provided the foundation for uncovering the invisible electromagnetic architecture of the modern world.